Great. Thanks everyone for coming, and we're very happy to have Alan Hammond from UC Berkeley, who will tell us about stability and chaos in last passage percolation.
Indeed, thanks a lot, Alex, and it is a real pleasure to be able to speak to you today, probability in the city today. So yes, joint work with Shishendu Ganguly, my colleague at UC Berkeley. Okay, let me begin with a story about certain general aspects of, complex discrete statistical mechanics, where we have a probability measure which is assigning weights, and then we can think about a Hamiltonian specified in this logarithmic way, and we can view that as a kind of energy landscape sitting over a surface, a background domain X on which we're charging points with probability. So a kind of landscape geometry in which the minima and local minima are significant because those are states which are assigned more probabilities. So we can have a phenomenon of a global ground state, the energy minimum, the most likely state, and then perhaps geometrically somewhat distinct but competing locations that are rivals to that status are competing near minimum, a valley elsewhere in the energy landscape. Just very qualitative themes. So three natural broad questions we can ask about such landscapes are question one, is the ground state super concentrated, a word that Sourav Chatterjee's perhaps introduced and popularized, and I'll be getting back to his work later on. This question then it can be expressed more precisely than this, but to give you an indication, it means, is it the case that the variance in a random statistic is growing more slowly than what would be predicted by a very classical setup? So for example, if you flip a coin n times, the variance is of course growing linearly in n according to a classical CLT. Superconcentration, roughly speaking, refers to situations in which the variance is growing more slowly than that, and the randomness is somehow more contained and concentrated than that. Question one there. Question two, are there multiple valleys in the energy landscape, several valleys that rival the ground state? Obviously, these questions need precision and context to make real sense, but qualitatively, at least here you see the ground state, the dotted line, and then several rivals to the throne that are somehow only just losing out, valleys in rather distinct locations that are very close energetically to the global minimum. And question three, does chaos reign? So this is an example drawn, I'm sure, familiar to many people, of the faces of the hexagonal lattice with the critical percolation equal chance independently of black and red. Is there a crossing from north to south in red? Is there a crossing from east to west in black? Well, chaos, this is concerned with, if we take that model, we can do dynamical updates to it by noising the bits and having them flicker from red and black and back again according to Poisson processes. And one can ask questions about the time scale, the number of bits you need to randomize in order to see significant changes. For example, if you begin with a red crossing north to south in a big domain, how much time, how many bits do you have to randomize in order to have a significant chance that that event is disrupted? Beautiful work around Oded Schramm, and particularly say work with Gabor Petra and Christoph Garbin about, well, 15 years ago now, I suppose, that treated this. Anyway, that's just another broad connection I want to draw attention to. So yeah, so is the ground state, if we go back to more the energy landscape situation, is the ground state sensitive to perhaps a tiny perturbation in noise that might be made? So that, imagine the landscape is flickering around in a somewhat random way. Is the status of the sort of king status of the ground state protected reasonably by a bit of a fluctuation like that, or is it rather vulnerable? And is a small amount of noise likely to disrupt its sensitivity versus stability? Yeah, okay, so Sourav Chatterjee's 2014 monograph treated a class of Gaussian models of disorder and said, in essence, that the three yes answers are equivalent to one another within a certain class of models. Superconcentration coincides with chaos, coincides with multiple valleys. And this is a theme and a backdrop to ideas in this talk. Yeah, okay, so we want to study, in fact, a more specific context. Sourav's themes were very general and broad, the emphasis here in the work with Shishendu is on a more specific model and a rather detailed study. So it's a dynamical form of last passage percolation, which I'll introduce in a moment. And the question of how much noise, if you start noising the environment, how much noise do you need in order to disrupt significant macroscopic statistics in the model? I'll say more shortly. The onset of chaos, anyway, the transition from stability to chaos, when does it occur? Yeah, so all right, let's at least let's warm up to this though by reviewing last passage percolation and the three aspects, the three questions. What kinds of questions might we pose in order to give questions that reflect those themes? So I'm going to discuss in this talk Bernoulli last passage percolation, and that is purely because I think for expository purposes it works well. The actual model study with Shishendu is Brownian last passage percolation. There's a lot of themes I'm trying to address here, so I prefer to simply adopt a model that's, I hope, nice to see and to think about in terms of the mentality of registering a talk. But understand that this is, the rigorous results don't apply to this model, but to another. Okay, so what is Bernoulli LPP? It is a very discrete model. We take the integer grid here and we assign 0, 1 bits to each vertex independently according to a fair coin outcome, heads or tails. So an upright path in this domain from 0, 0 to n is, as you see, a northeast going path. Its energy is the sum of the bits along the route. Just collects all the zeros and ones. What's the total? That's the energy EP for the path P, the upright path P. Okay, so a random assignation of energy to every upright path. So the geodesic is the path of maximum energy, gamma n, capital gamma n, and m for maximum, mn is the maximum energy. A detail is that for this model there are several maximizing paths, several geodesics. I'm simply proposing to ignore that, blatantly ignore that discrepancy for sort of expository purposes. I will refer to the geodesic. The underlying model we work with doesn't have this non-uniqueness. Anyway, Mn is the energy of the geodesic on that given route. So superconcentration is reflected here by the growth in the geodesic energy as n rises, as the domain rises. There's linear growth, as you would expect, in the number of heads collected. It takes the form of there are 2 n points, or maybe 2n plus 1 points on each one of these parts. So you would expect slightly more than half of them to be heads, because we're trying to collect as many heads as possible. That's reflected by the fact that A is strictly bigger than 1. Now, the fluctuation on top of that is not the Gaussian predicted, the central limit theorem predicted n to the 1/2. That's classical. It's n to the 1/3. And then we can write a form of scaled energy, if you write, in the form of this, the guise of this Wn statistic, which is that Wn then is now a tight and non-degenerate sequence of random variables. So we sort of grab hold of the asymptotic randomness, the scaled randomness with the statistic. Specifically, the variance is of order n to the 2/3, and that's obviously less than the CLT type n. So this is a phenomenon of superconcentration in a very quantified way. Oh, and as I say, all of this is actually true for integrable models. This is what's expected for this model. The energy landscape, the second question, the energy landscape of LPP. Well, one question we can ask in that regard is what's the correlation between geodesic energies on different routes, where one route is the original one, and another route is one where we perturb the latter endpoint horizontally by an amount x. What kind of question can we ask here? Well, here's the picture, okay? So original picture in black, perturbed picture in blue, 2 energies then, maximum energies on the black and blue routes. What's the scale of x that has to be chosen in order to see genuine changes? So a correlation that's θ1, you know, is 50%, bounded away from 0 and 100%. So the scale of this is of order n to the 2/3. Of course, these are, I'm sure, familiar to many people. Forgive me if this is something you're very familiar with. I'm trying to build the themes. N to the 2/3 is this distance that's very characteristic in these problems. So that suggests a scale picture, you see, where if the original routes are indicated on the left here, then it's nice to scale them affinely so that you have the correspondence you see here. So then the original geodesic is now in correspondence with a path that runs directly upwards to 0, 1, and the alternative blue route to 0, 1, you see. So that's a nice sort of scaled representation, a scaled picture for the geometry of what's going on here. And if n is large, so you don't see the lattice on the right, I can lazily say, I mean, I didn't want to draw it, but you know, the picture on the right is a scaled picture. A scaled geodesic is a word I tend to use that's not uniformly accepted is polymers for that. It's just a more compact term. So you see well, they're now they're both black, but black and blue are moving up to 0 and x there. So the energy then, it's natural to view that scaled energy I introduced. There's now WNX. It's a function of x. There's a whole process going on really. So that the words written in red, random but unit order scaled energy, just as we have a scaled path in the right picture, it's natural to say that it has a scaled energy, and that's WNX if it's going up to location x. So we have a whole kind of scaled environment, or some analog of the landscape geometry I mentioned. Yes, well, that's what this slide says. Okay. Yeah, all right. So we've got the scale picture of the polymers, as I say, the scaled geodesics. They form actually a tree structure. There's a kind of a simple argument for why, when things join together, they stay together. So you have a nice tree structure of people coalescing down to 0. And so then you can actually plot the scaled energy of the polymer running up to n location x as a function of x. That's a random function. It's the function mapping x to WNX. So that's what you could call the polymer weight profile. It's a representation of the scaled energies as you vary the top endpoint in scaled coordinates and keep the lower endpoint fixed, the so-called narrow wedge in KPZ. Yeah, okay, so we then take a high-end limit of that, interested in things like universality. That is the parabolically shifted version of the Airy 2 process. And here we have these kind of landscape geometry questions. We have a peak energy. It's now an energy maximum rather than an energy minimum. That's the relevant analog. And we have some sort of potential rival peak nearby. So we might want to investigate quantitatively, you know, probabilities of rivals and so on in this scaled picture. So yes, all right. So building up then, I suppose, to question 2 then, having introduced that setup, what's the probability of near twin peaks, of a rival to within order epsilon of the energy maximum, which is geometrically distinct. So in scaled distance, at least 1. So in this picture, you know, the suggestion is that the maximum and the rival are at a unit distance. If they're extremely close, then it's inevitably going to happen like this. But if we fix small epsilon and demand distance 1, we have a genuine pretender to the crown that's distinct on a distinct lineage, if you want the analogy developed. Right, okay, well then that's the claim. Now the probability of this epsilon twin peaks illustrated here is of order epsilon. So the proof idea for this is coming up. So the proof profile resembles closely Brownian motion to unit order on unit scales. So the estimate is inherited from Brownian motion. It's not hard to see that estimate is true for Brownian motion. So that raises the question, why does the profile closely resemble Brownian motion on unit order scales? So here we get to embedding the parabolic Airy 2 process. That is the limiting distribution of the top curve in this scale picture, WNX, and when n is infinity formally. So we can embed that as the uppermost curve in a whole ensemble of curves, continuous random curves, which I suppose is here. This is the parabolic version of the Airy line ensemble. This is via the RSK correspondence. I'm not going to explain it now, but there's a canonical embedding in this nice system that has a nice joint property, a resampling property, that if you wipe out the top curve on a given interval, it has a nice conditional distribution involving putting the curve back in, given its endpoints as a Brownian bridge, a condition to stay above the curve below. So there's a sort of Brownianity jumping out at you, Brownianity and mutual avoidance jumping out at you in the definition of this resampling. And the Brownian-Gibbs property introduced with Ivan about 7 years ago is now becoming quite a useful tool for various aspects of probabilistic analysis of KPZ, including specifically the Brownianity of the Airy 2 process. Yes, so this work, Twin Peaks, is actually a phenomenon we've taken further in study with Konstantin, Milland, and Ivan, but the specific result here is due to a joint work with my students Jake Calvert and Milland Higby. The Twin Peaks probability is of this order because of a very close comparison between the area 2 process and Brownian motion that's developed in this work. Yeah. Was that a question? It was a... No? Okay, so then I suppose on to the third question. What of chaos? So we have a dynamical version of Bernoulli LPP. I chose Bernoulli LPP for the talk because it's quite nice to explain, for example, what the dynamical version is. The bits are independently updated at rate 1 Poisson times, and then I suppose new heads and tails decisions are taken at each time. A new coin is flipped. So at any given time, we have at time 0, we've got a copy of static Bernoulli LPP, the original law, and then that, of course, has a geodesic, which we now has a time dependence we denote with the 0. You see, it has an energy Mn as a function of 0 now. But in blue, at a later time, things are flickered around a bit. We have a potentially new geodesic and a new energy. Okay, so a function of t now. So how to measure the fragility of these objects to the passage of time? For energy, we could look at the covariance function. It's the deterministic function, which is the covariance between the geodesic energy at times 0 and t. Or a more geometric view is to focus on the geodesics and to look at the degree of overlap they have. When t is 0, there's obviously perfect overlap and coincidence between the geodesics, and as time evolves, they go rather separate ways. So we can look at the number of points in the intersection. It starts at 2n plus 1, I suppose, and drops. So that's a random function. Yeah, okay. So, you know, the covariance starts at the original variance, ends to the 2/3, and in principle, it's easy to see it will tend to 0 because ultimately you'll have an entirely independent field of randomness. The, you know, it starts at order n, the overlap, and then there's an argument that the high t limit with an independent environment, the overlap is n to the 1/3. I won't give that argument now, but anyway, you have this sense of decrease. I mean, one function is random, the other's deterministic, so it's a sort of slightly average plot or coarse-grained plot in the second case, but you have the sense of decrease. The question is, when does the decrease rarely occur in some case, in some sense? So the theorem of Chatterjee says that for a dynamical version, in fact, of Brownian LPP, which I'm not, in fact, going to define, the transition from stability to chaos measured by geodesic overlap, we take the geometric view of the latter geometric overlap, occurs on the scale that t is n to the minus 1/3. Now, this is not a precise statement that's on the next slide, but the takeaway here is that the dramatic changes happen when t is n to the minus 1/3. So only a small fraction of bits. This corresponds to each bit being re-randomized with probability n to the minus 1/3. Only a small fraction of them are being so randomized. So what does it actually mean more precisely? The stable regime where t is less than n to the minus 1/3 is one in which it is typical that the overlap between time 0 and time t is macroscopic, and that a positive fraction of points in the original geodesic are in the new one. That's represented by the first statement. We see a departure from that into a chaotic regime when t is significantly above n to the minus 1/3, a slight imprecision, I suppose, in what that means in what's written here. But anyway, in that regime, it becomes typical that the overlap is little o of n. So a remotely typical point on the original geodesic is no longer on the time t geodesic. Okay, this is the principal theorem that is not stated with total precision, but I hope the fundamentals there. This is the aim of my talk, to tell you something about how we prove this. In reality, the focus will be on, well, let me just get on with it to some extent. There's quite a lot to get through in a way. Signpost to the proof. Okay, to show the transition from stability to chaos, let's back up for a moment and think, if we're trying to prove a theorem of this type, how could we go about it? We want an order parameter. We want something that we can say is high on one end and low on the other end of the transition. We've got two choices for that: energy or geodesic overlap. So there's a subcritical and a supercritical regime. It's not yet clear why these are correct. Scale into the minus 1/3. Let's just admit that for now. So if we were working with energy, we could try to prove subcritically that there's not much change in energy. It's little o of n to the 1/3. This is unscaled, so that's, you know, n to the 1/3 is the scale of the energy fluctuation, the genuine randomness in the system. And then that goes up to being, you know, of order, presumably, n to the 1/3 supercritically. That's what one would expect if it's a genuine transition. For geodesic overlap, if there's not much change, it's a high overlap of order n, most points, or 50% of points to share. And then low, as time goes on, it becomes littler then. So we have proven the situation on the second line with geodesic overlap, but there's a strong interaction with ideas on the first line as well, in fact. That's represented here. So the three-step game plan for proving this is we harness Sourav Chatterjee's monograph to deliver an understanding that there's low geodesic overlap in the supercritical regime in the first step. In the second step, in related ideas with some harmonic analysis, we show that there is not much change subcritically for energy. And then the vast majority of our attention in the work with Shishendu is on the substantial technical component for us is to then show with an assist from step 2, step 3, that there is in fact high overlap typically in the subcritical regime between the geodesics. And then obviously 1 and 3 deliver the theorem, okay? So actually in terms of the talk, in order to deliver you the ideas, it's going to be quite a lot of focus on the steps equally in terms of what we are actually doing on a day-to-day basis. During a fairly lengthy period we were exploring this and writing it up, we were more working on step 3. So there's a slight change of measure from our experience for the talk, but the other elements are important. I suppose they reflect, I suppose, Sourav's experience, for example, in doing that work. So we'll be talking about 1 and 2 certainly to begin with. Let's look at step 1 and tell you something about how this is done. So this is the supercritical phase where T is much greater than n to the -1/3. As I say, it's not yet clear why this is the correct exponent. So the aim is here to show that the geodesic overlap is low. So Sourav's theory concerns Gaussian polymer models. So Brownian LPP is an example of that. Anyway, I want to extract from his theory the key point, which is a beautiful formula, which is that the variance of the geodesic energy on this route from 0, 0 to n is given by this exponentially discounted mean of the geodesic overlap between times 0 and t. This is the takeaway that is driving what we need. There's also a monotonicity statement. This statement is incompatible with the possibility of high geodesic overlap supercritically, simply because the e to the minus t in the relevant regime is essentially absent because t is small. So because the variance is of order n to the 2/3, it means that things would simply be too big on the right-hand side if it were the case that we had moments supercritically at which we typically had high overlap. So on this basis, we pretty directly learn that, that the mean of the overlap must be falling rather precipitously from its original order n as t advances through this scale n to the -1/3. Yeah, so that's point 1 in the game plan. For step 2, so how do we go about arguing that subcritically we have energetic stability? So here I'm going to move to a theme of harmonic analysis. Actually, what we did in the work was to invoke aspects of Sourav's theory again. That this is a kind of cousin theory, and I want to mention it. I think it's a beautiful theory. It connects to things like the percolation, dynamical percolation I mentioned earlier on. So I'm just going to sort of spend a few minutes talking about these ideas. They're not actually the logical route we used, but they're well suited also to Bernoulli LPP. So let's look at some of the discrete harmonic analysis of Bernoulli LPP. Well, in a moment anyway. So the statement we're trying to prove is this one, right? We have this, maybe a slight change in where the t appears, but we have this MNT. This is the geodesic energy at time t for this route. So this is the statement that I'm going to try to convince you of, this inequality in the middle of this slide. If we move to the more scaled coordinates, where tau in the blue on the bottom of the screen is a more scaled notion of time. So think of it being somehow but fixed but small, sort of representing a subcritical scale time, then you can see from this and an understanding what the fluctuation in energy is, it's n to the 1/3, that you know, there's not been much change in energy maximum energy between time 0 and time t. So the inequality in the middle of the screen is what needs to be justified. So here we get into the discrete Fourier analysis. So we have lambda n, this bit space, and then you see the geodesic energy is a nice map, as you can see illustrated here, from the bit space 0, 1 assignations to the number 4, in this case, 4 points on the geodesic in this example. Yeah, so then it's a Fourier thing. So to each subset of the bit space, we have this nice Fourier Welsh type function. It assigns to a particular assignation of zeros and ones the value either +1 or -1. It's essentially a parity consideration associated to each subset S. Are there an odd or even number of zeros in the set? Yeah, so that's a nice orthonormal basis of L2 for functions mapping the bit space to R. So that means we can write any function we please that's a function of the bit space, including the geodesic energy, as a decomposition with coefficients alpha s in this Fourier basis. And I think the Fourier coefficient for the empty set is the mean of the function. Okay. So Pascal's formula tells you that the variance of your function is the sum of the squares of the non-zero indexed coefficients. So that then leads to a very nice probabilistic definition of the spectral sample. That's an actual random variable that takes values in subsets of the bits, random subset of the bit space, under a law which we can call Q. That's canonically associated in this rather interesting way to any given function, including the maximum energy. So what is that? Well, anytime a probabilists see a collection of numbers that add up to 1, it's tempting to introduce a probability measure. So there it is. Pascal's formula tells you that those numbers add up to 1. Okay, so the fundamental role of the spectral sample in studying dynamics is that the covariance between the energies at time 0 and t is given by this exponentially discounted sum of squares of the coefficients, related formula for the correlation. So you see the basic message is that if the spectral sample is typically, it's a random sample, it's a random subset of bits. If it's typically rather big, what that means is that things are changing quickly because that sum just isn't stable. When t reaches order 1 over the typical size of the spectral sample, you're getting wiped out by that exponential term. It's the low modes that are stable. So if there's a lot of mass in the high modes, it's a chaotic situation with a quick onset of chaos. So that's why we're concerned with the mean size of the spectral sample, the mean value of the spectral sample under the indexing notation for just the mean size of the spectral sample. The claim is it's n to the 1/3. And then essentially, I won't carefully go through this, it's simple to go through it. If we wanted Jensen's inequality implies on this basis that we have the inequality we seek. So it comes down to what's the size of the spectral sample typically, and the intuition is what I said, that you get wiped out on the higher modes on timescales that are reciprocal of this. This is n to the -1/3 is the reciprocal scale of the typical size of the spectral sample. Chaos is occurring after that. So, all right, so, okay, so essentially with a little skipped application of Jensen's inequality, subcritical energetic stability has been reduced to deriving the fact that the mean size of the spectral sample is n to the 1/3. So 3 steps now to this formula. Okay, so for any bit, you can consider the modified function in which you take the bit space and you flip its value at v. If it's 1, it becomes 0. If it's 0, it becomes 1. And that may or may not change the value of the geodesic energy. But the claim is that when we sum over the bits and look at the mean squared change that results from that flip, and then divide by the variance, we have this formula for the mean size of the spectral sample. So the randomness involved here is, of course, still the, each bit is 0 or 1 with equal probability, and then one of them gets flipped. So that's the randomness of which the mean is being taken in that summand. Okay, so that's a formula I'm claiming. I should do something to justify it. So what is the mean size of the spectral sample, the left-hand side of that formula? It's, of course, the sum over the bits of the probability that a given bit is in the spectral sample. And then by the definition of the spectral sample, well, we have this formula involving the subsets of the space that contain V and the square coefficient there. So if we're going to prove that formula obviously has some similarities to what we're going for, it has a shared denominator. So what we would need is the numerator, there's this factor of 4, for a given value of V, this expression at the bottom. Okay, so I need to justify that to some extent. This is simple linear algebra tricks and things at this stage. So if Mn has this representation, Mnv has a modified representation where we've slightly deformed the definition of the Fourier-Welsh function by a parity flip concerning status of V. So then we can do things like take a difference and square it up. I'm trying to adopt a speed that is perhaps just slightly uncomfortable for analyzing and confirming these details, but hopefully the overall flow of this is clear, that we see some instances of V not mattering and others where it does matter. So this expression B, it has this consideration of whether the set contains V or not. So when you look at the form of the expression, you have a cancellation and a doubling up, the doubling up occurring for those sets that contain V. So yeah, it's probably better reflected on for a few minutes privately rather than trying to do this live. But you know, this is a fairly simple formula you can derive. So that then means we've got ourselves to this situation. We're trying to show that this left-hand side is of order n to the 1/3, and we've got a nice formula. The way it will work is that the formula on the right-hand side, the brown will be of order n, and the blue is of order n to the 2/3. That's the variance. As I say, I'm sort of assuming the kinds of KBZ scalings for the Bernoulli model. It's actually the Brownian LP model we work with, which is integrable, so we know this kind of stuff for that. Anyway, n to the 2/3, if we accept that as given for the denominator, it's my task to try to demonstrate to you, to convince you that the brown circled object is behaving when n is large, of order n. Okay, and then that will deliver what we claimed and yeah, what we used. So, all right, why is that true then? So you've got a particular geodesic there just statically, and then of course it has n elements on it for which flipping makes a difference. I mean, or it depends on whether they're 1 or 0 to begin with, but many of them are 1 to begin with. So if you flip them to 0, you're going to change the outcome. Or in fact, all of them will change if you flip. So the issue is that's fine for a lower bound then. All those terms are unit order. The squaring doesn't make any difference to these individual changes there. N bits change, so you have a lower bound of order n. Why is it an upper bound? So that's in blue. We wish to argue that I can look at other bits of the geodesic, but I want to argue that there's only a comparable order of off-geodesic vertices for which it makes a difference. Many vertices are just deeply uncompetitive, nowhere near a geodesic. You flip them on and you're not going to rival the status of the geodesic. We want to argue quantitatively that it's basically the ones on the geodesic or perhaps very nearby typically that dominate. So yeah, all right. So if we go out from the geodesic by a distance k, so that's the length of that anti-diagonal arrow, we want to argue in this situation that the probability that that particular V is where it's at, is pivotal, is making a difference, is of order, in fact, k to the -3/2. Yeah, so if you do that, what you'll be doing then, if you accept that premise, then if you sum for a particular diagonal coordinate, if you sum along the anti-diagonal, you have a convergent sum. So then that reflects the fact that there's not this extra order of term, it's just on the diagonal and nearby in practice, the unit order kind of effect that creates, when you then sum over the diagonal coordinate, the overall order n that's being claimed. Okay, so that's what I'm supposed to justify then. And this is getting perhaps for this talk a little technical, so perhaps just a few ideas and impressions you may be left with from this, but let me attempt something, okay? So I've moved to more the scale picture, or at least I've twisted by 45 degrees. So now that anti-diagonal line in the middle, I just choose it to be the half-life time n/2. is horizontal. So V is at that distance K, and we have the nice geodesic running right through the middle. It has a preferred route at its midlife time. So you can then have a look at two kind of nice energy profiles, which are indicated by up arrows and down arrows in black and blue on the lower half of the screen. So one of them reflects the amount of energy you collect from the birth to the midlife time as a function of this midlife time. That's a certain energy profile. That's the black over on the right, upper right corner of the lower black image. The random walk image there is intended to denote that profile. And then the other way, it's from the moment of departure, we can view the energy you're collecting in the second half of your life as a function of this coordinate. Now, it's a little involved, but it's convenient to plot that function in a sense upside down with a minus sign, and then to shift it vertically. So it's just touching, but not crossing the black curve. And then the interpretation of the, if you instead, there's a preferred route here through the midlife time, through the middle there, right? If you insist instead of going via V, you're going to pay a certain shortfall cost. Now that cost is the distance between the blue and the black curves in the upper right image around where the brown arrow points, right? So that's a gap. Now that gap could be 1 or 0. That's the key event. It's a twin peaks. It's a near touch event that is relevant here. What's the probability of that? As I say, it's a little involved and quite a lot to take in, but these are sort of the geometric ideas with these curves that one sees. Yeah, all right. Well, okay. So then it's at this stage of a heuristic. It's developed rigorously for Brownian last passage percolation. The black and the blue are essentially random walk objects. It's to do with the invariance of things like the Bernoulli law in, say, totally asymmetric exclusion. It reflects the random walk nature of the black and the blue curve. So the probability, if I have two random walks that are conditioned not to meet again, that they come within, say, distance 1 at time k, is you can check k to the minus 3/2. That's what's going on. Yeah, okay, so all right, that's a flavor of that. So that brings us to the situation that we have here. If we're trying to prove the theorem for geodesic overlap, what we've achieved so far is that the transition, coherently with the transition, we have the phenomena we expect in the southeast and northwest of my box. We have low geodesic overlap supercritically. We have not much energy change subcritically. So the technical challenge we faced was then to prove with these inputs and as a complement that we actually have high geodesic overlap in the subcritical regime. So that's the third step. Yeah, okay. So here we use step 2 in quite a strong way. We use the fact that there's not much energetic change subcritically to prove that there is high overlap in that same regime. And we do that using a technique we introduced called we called it the proxy. So let me just tell you a bit about that. Okay, so let's kind of imagine a situation that is at least characteristic of our kind of counterexample regime. Suppose that we're trying to prove high overlap subcritically. Suppose to the contrary that we had low overlap between the geodesics at some subcritical time. So if we draw things as I often prefer to do in this kind of scaled picture that I introduced, rho can be a label for the scaled geodesic, or tend to call it polymer. So yeah, it might be, you imagine, fairly typical. The way you're going to secure an outcome with low overlap is that people go rarely on different routes. They're born and they die in the same location, but they spend their lives somewhat apart. This is by no means the only way this can happen, and we had to analyze plenty of other cases as well. But it is perhaps intuitive at some level that it's a typical way this can happen. So it's kind of an important case. So this kind of picture, what's wrong, in other words, with this kind of picture? We're trying to defeat this picture. We're trying to show that it's, you could say, I suppose the probabilist contradiction is to show an event is low probability. That's what we're trying to do. Yeah, okay. So, okay, So we have a good understanding of static scaled last passage percolation in integral models via things like the work I mentioned, well, many things, but including the work with Jake and Milland I mentioned, a strong understanding of the Brownian form of these profiles. So what it's tempting to do in this new territory of dynamics is to try to take a shadow of the time t picture and in some sense transport it to time zero. So if something that we believe is peculiar is happening between times 0 and t, we find that it has a projection or shadow at time 0, which is a provably rare event that we can then use our understanding of static percolation, as I say, to show a static last passage percolation to show is provably unlikely. So that's the role of the proxy. The proxy is a device for transporting the substantial characteristics of geometry and weight of the time t geodesic to time 0. So yeah, the proxy, which is indicated, the sort of t becoming 0 symbol is used in the superscript. The proxy is mimicking broadly the root of the time t scale geodesic, but in its time 0 weight, it is mimicking the time t weight. It's close to the time t weight of the time t geodesic. So it performs two feats of mimicry, geometric and energetic. How does it work? Well, the proxy is basically formed by, the black curve is doing its thing at time t, choosing the best route it can. It is actually hopelessly uncompetitive. If you choose that route and ask what is its time 0 energy, it's just terrible. It's some completely uncompetitive function. But if we choose a coarse-grained description of it, basically just picking naively, we have to do something a bit more subtle actually, but naively we just pick points along it at regular intervals. And then the red are interpolating time 0 geodesics. So here we will have an object that substantially mimics the geometry of the time t object, but because it moves locally to maximize time 0 energy, it reports a pretty good outcome in terms of time 0 energy. Specifically, well, I'll get back to it in a minute. Okay, so if we, all right, so in terms of preserving our picture, this is the picture we're imagining that we're trying to defeat, the substantially different routes adopted by the geodesics at times t and 0, with time blue being time t. So that typically forces something that in some sense looks just the same. You know, there's good mimicry geometrically as you move from original time t to proxy, from blue to red. Okay, so you won't actually in some sense see much change viewed in the right coordinate system. Yeah, okay. So again, the proxy then inherits this characteristic from the upper picture of having a substantially different life experience, a different geometry to the black time 0 geodesic, scale geodesic. All right, now what's nice though is we can harness our understanding of subcritical weight stability to say that there's not actually much change in energy between time 0 and t. Kind of a little of one difference, and because the geodesic, the proxy is constituted of these kind of local patches that are geodesic at time 0, you can actually make the same comment for that object. In fact, so what that does is it creates an outcome in which the proxy is close to the time 0 geodesic in its time 0 weight. And then this is geometrically significant in terms of our understanding of static scaled last passage percolation. It's a picture that's similar to the one with the two random walks, one of them upside down, and the business of whether you have a near touch or not. So again, perhaps it's a little rapid, but it's the same ideas though. We have this midlife line, a half, and then we monitor scale energy. What's the best you can do starting at 0, running up to this line? That's the lower black curve in that lower picture. And then in terms of finishing at this moment and monitoring maximum energy, we can plot this function And it's convenient for this representation to actually draw that curve upside down, in fact, so with a minus sign, and then translate it vertically. So you have a nice touch, but no cross. And that point at which you touch in the lower image is, you see the x coordinate is the place where the geodesic runs through. This is how this goes. And then what's happening is that over on the left side of that lower image, the gap between the curves, which is sort of near those brown horizontal lines, that distance is the cost and the shortfall in energy you get if you insist on going on this other route. And that's essentially what that shortfall is, essentially the difference in energy between the geodesic at time 0 and the proxy, with 1 or 2 extra errors, but that's essentially true. So the point is, we understand those things to be, we understand that error, that difference to be small. So there's something geometrically significant in the static copy of scaled LPP, that you have a near touch. So the near touch event is essentially the same as the Twin Peaks event. Why is this? You see, the individual curves look strongly Brownian on unit order intervals, and they're independent. The randomness in the first half and in the second half, these are independent. So this is a question of something like a difference of Brownian motions. It's just a Brownian motion of double the variance locally, double the diffusivity. So if we look at that difference, you get a picture that's more like this. A near touch event for the difference of the profiles is a Twin Peaks event. So you have the energy maximum, of course, in this case on the right, reflecting the root of the geodesic on the right, and its rival in energy over on the left, that's the root of the proxy, and it's a close rival to within a parameter that I've not labeled here, but it speaks to, you need to do this in a bit more detail with notation for me to tell you what the exact closeness is, I suppose, but I mean, I try to advocate that there is this closeness. So just to use the language of earlier on with Twin Peaks, that closeness was epsilon, and as we discussed earlier, coming from the work with Jake and Milland, that's of order epsilon, that probability. Okay, so we took something that we expected on the basis of whatever informal understanding we have, whatever intuition drove us to this point, to believe would be a rare event. If we have low overlap, it might be typical that we have this big departure in the midlife, and then we transported that picture so that it typically forced a Twin Peak event to occur in the static randomness of an individual copy of Brownian LPP, or in practice Brownian LPP. Yeah. Okay, so yeah, well, this is probably largely what this says. In summary, the proxy transports the geometric scenario typically forced by overlap between the time 0 and t scale geodesics for t subcritical for our time to a provably rare Twin Peak scenario at time 0. I've given this talk a couple of times in summer. I always have this habit of saying something verbally and then finding that I wrote it down on the next slide, but no matter. Okay. So that's it really. So there you see you've got box 3 ticked. It's a lot of work that went into it. So there's things that are hidden here. As you can imagine, the geometry of this situation is just one example. You can have alternative geometries of coming back in, and you can achieve low overlap by a whole string of sausages with brief interludes of shared time. It's intuitive perhaps that that's more painful to do, and I think we prove that, but there's work in that. So anyway, you've got the main theorem on that basis, and I guess that's I guess that's the end of my talk. I'll stop there.
Thanks a lot. Other questions? Maybe I'll ask a question. In the case where you said there's like this order n amount of overlap, do you expect to know that to be sort of, is it n minus little o of 1, or is it really some fraction of?
Oh yes, so that's quite a good question. So I think it might depend on the model. So if we were working, let's work with Bernoulli LPP for the time being and just heuristics around that. In that model, I think if you're significantly below the transition point at a small constant multiple, I think you probably expect that to tend to 1. I mean, at least in Brownian LPP, in a sense, you have instantaneous changes to you might, in a discrete model, your microscopic structure is somehow very protected for a long time. In Brownian LPP, your microscopic structure actually changes instantaneously. Yeah, I guess it's the case that if you take tau scale time, whatever it is, t times n to the -1/3 is that, no, t times n to the +1/3, then you can ask what the overlap is divided by n as a function of tau. And I suppose for these models, you expect a function that tends to 1 as tau tends to 0, but I'm not actually 100% sure about that. It's a nice question. I mean, of course, the question is also around the topic of the next phase for this research, were it to be pursued by others or by us, would be, I suppose, around this question. And I was slightly imprecise in the main theorem about what the meaning of the symbol much greater than is. But it would be nice to develop things to have a sharp window with these kind of questions, I suppose, being addressed.
I'm trying to do a positive temperature version of all of this picture. Are all the pieces there, or are there kind of technical things that are missing?
I haven't thought much about that. I mean, you have to think about, are there clear definitions? There are, people do study overlap for, but in a sense, you have 2 levels of randomness at positive temperature. So if you ask questions about overlap, there are clearly accepted answers to what that means. Are they?
I think in like spin glass literature, people certainly have dealt with this.
Yeah, well, no, I mean, it's certainly a beautiful direction. Yeah, well, I suppose like we turned, airy line ensemble into KBC line ensemble, that would be a vector that one could try to take. It would be probably quite a big project. Yeah, with even the definitions, I'd have to think about what the right definitions are for overlap and so on. It would be interesting to maybe back of the envelope that and see if the n to the -1/3, for example, passes to positive temperature in the scaled sense of finite KBC time. That might be quite fun to do as a mini kind of heuristic thing to begin with, I suppose. I might think a bit about that. I don't think I can say anything very bright about that live, but I think that might be fun to think a bit about.
Alan, can you comment why the box which is not marked with the V is more challenging than the other boxes? This is not what I would have imagined to be the hardest.
So the box that is not marked with a tick, why is that?
Yeah, why is it hardest? Not why is it not marked. It's not marked because you didn't prove it yet, but why is it the hardest?
I'm not going to be able to say anything about why. I mean, it's certainly a good question to explore. Why is it that how do you prove that when you have supercritical time, there's a lot of energy change? And there can be different strengths of the statement there. I mean, we did think about this for a while. It might be that the idea is that, I mean, one thing there's been a bit of a restriction up to now is that strong understanding of Brownianity tends to work better in narrow wedge situations because you have the Brownian-Gibbs property. I vaguely remember that, but you see, that's becoming broader now because of partly because of work coming out of this DOV paper from Toronto. Sorry, I'm not giving up. I don't really, we did look at it and discuss something, and I'm just free associating about it. And I remember we were proposing some resampling arguments that sort of moved away from the narrow wedge. That's just what my mental image is of that. I can't actually remember very clearly at the moment. So I can't give a very good answer basically to the why of why it's difficult. Okay. It is, it's a good question, and obviously I invite people to register that, and that is a fun direction. And as the other questions are as well, in fact, these are, I think, good lines of inquiry. So it's definitely a good question to explore.
A second question, which is a bit more technical, you get this decay of k to the minus 3/2 along the anti-geodesic, but it looked to me that I thought that your proxy going back to time 0 was extremely qualitative. And can you mention a little bit how do you recover the power, the nice power 3/2 from this? Maybe I need some point.
I'm actually not sure whether we do that. I mean, because the earlier, that idea has come up very resonantly in two contexts in the talk, but the first context is a heuristic argument really about a non-integrable model on a very microscopic scale, whereas this is a scaled picture. I mean, for example, in this picture, the distance you see between the king and the rival is a unit scale distance. So that's, I mean, the biggest relevant scale in the system. It's entered the 2/3 microscopically. So.
No, but if you go back in your slides a little bit, there was a point where you mentioned more.
That one?
Yeah, here, there was explicit power.
Oh, that's right. But, well, the explicit power in the, I guess they line up. Do they line up? The explicit power in the other context is the power of 1 that you see in the epsilon to the 1, the probability of twin peaks.
Right.
So I guess they probably line up because there's a 2/3 hidden in the transform.
Oh, I see.
You know, there's an enter the 2/3 so it becomes a 1. So I assume that they line up for that reason.
Okay.
Yeah.
Thank you.
No, that's right. Yeah, that's right. I mean, they both come down to considerations about whether they're random walk or Brownian motions. If you take the difference, what's the probability that one of these objects comes close at a given point? So this power is coming out that way. Well, yeah, there is a little bit of a difference though, actually, because you see, k here is given. It needs to get summed over. If you want the analogy, it's more relevant maybe to sum this from k to 2k. Because the twin peaks, the later twin peaks, I'm just saying, is there a rival out there for the king? The king doesn't worry about the precise location. So in a sense, you're going to have to sum that out over a dyadic scale to get an analog, which would point more to a power of k to the minus 1/2 as being analogous.
Yeah, okay.
Which...
Okay, so the 3/2 is really a derivative of, imagining derivative of something more coarse, which is n to the minus 1/2.
Yeah.
Okay. Thank you.
Any more questions? We can thank Alan again.